Now let's move on to second order systems. So far you looked at first order systems that contained a single energy storage element such as a capacitor. So a circuit containing a voltage source, a capacitor, and a resistor was a first order circuit. Now we will look at second order systems. So in these circuits you will have two independent energy storage elements. So for example, you might have a capacitor and an inductor, or you might have two capacitors that are independent of each other. Now, in such systems, we are going to get dynamics that are governed by second-order differential equations, not first-order differential equations. So to study second-order systems, I encourage you to review complex algebra, which is in Appendix C of the textbook. So you need a little bit of that stuff for time domain second-order systems that we will cover in the next two sequences. And then we'll use a lot more of complex algebra in the sequences for next week. And in case you're wondering what this bridge is doing here, in case my art is not all that good, this is a bridge after all. This is a suspension bridge. And in case you're wondering what this bridge is doing here, well, I will keep you in suspense. Haha, that was a pun. A bit of a poor joke. You will find out what suspension bridges or bridges have to do with second order systems later on in the course, and you will see some surprising, exciting stuff. All right. To motivate the study of second order systems, let us look at a very familiar situation. Okay, that of a inverter driving another inverter. Okay, we saw this as a motivating example in our first order systems. Well, it turns out that under certain conditions, this is a perfectly good system to study for second order systems as well. So let me draw out the equivalent circuits for these two inverters. So bear with me for a couple of seconds while I painstakingly draw it out for you. Okay, so let's have a 5 volts supply, Vs. I have a load resistor, and in this case, let's assume it's 2 kilo ohms. And I have my MOSFET. Okay, so this is my first inverter. And let's say my MOSFET is driven by some input. And this input is some sequence of ones and zeros. Let me call this node A. This MOSFET drives a second inverter. Okay, this inverter drives a second inverter. Let me draw that inverter here. There we go. This is also 2 kilo ohms, and this is also 5 volts. And here is where I take the output C. So this is my input A, my intermediate node B, and my output C. So I'm going to connect my first inverter to the second inverter input. Okay, and in here, just to be clear, let me connect up the ground nodes just to show you the connections very, very clearly. So let me mark this node as B, and of course this node is marked C. Let me also draw out the some of the parasitic capacitances and so on that we see in this circuit. So the reason I call them parasitic is it's not something I usually see, but it's something that appears whether I like it or not. And so here is my capacitor between, and let's say this capacitance models the gate to source capacitance of the second MOSFET. Okay, it may also include the capacitance of the wires connecting the output of inverter A to the input of the second inverter as well. So all of that, put together, let me just call that CGS. Okay, there is my capacitor. So here is where I show you the gate to source capacitance of the MOSFET. Okay, let me mark these nodes with some colors. So as I draw them out, I can use some nice little colors to show them. So let's mark this. Let's mark this with yellow. Okay. Let's mark the node B with green, and let's mark node C with what if we say purple? Okay, there we go. So I'm going to mark these nodes with these three colors so that when we draw out the waveforms, those will be pretty clear. So here is our circuit, and this is our MOSFET inverter driving another MOSFET inverter. So now what I could do is I could look at what the waveforms are going to look like at A, B, and C and see if they match our intuition. So based on what we know so far, I can draw out the waveforms for this little circuit. So I'm going to plot the waveforms at A, and that is going to be VA. Waveform at B, that's going to be VB, and the waveform at C in purple is going to be VC. Okay, so let me start with the waveform at A, and let me pick yellow. So let's say the waveform at A is some square wave that looks like this. 0 to 5, back down to 0, and then I go up, and then back down to 5 again, and then I keep going. Okay, so that is my waveform at A. Okay, next, let me plot the expected waveform at B. And notice this little capacitor here, and let's say the RC time constant here is pretty large. Okay, so what I'm going to see for at VB, so the waveform at B, call that VB, is going to look something like this. So my as I apply a low voltage at VA, I'm going to get a high voltage at VB. And then when A jumps up to a high value, B gets pulled down low, so the B node gets pulled down low, and it goes down pretty fast. And the reason it goes down pretty fast, as you will see in this demo, is that the on resistance, okay, on resistance of the MOSFET is very, very low. Okay, so B will go down pretty nicely as you expect, pretty quickly. Then I go up here, and now when A rises again, okay, so when VA rises, what happens? When when VA falls. So when VA falls here, the first transistor is going to shut off, and the node B needs to be pulled up to a high value. But now notice that the capacitor is initially charged to a low value, CGS, and it needs to charge up through the 5 volt and the 2K resistor, and there's the CGS. So in this case, let's assume it's a pretty large time constant, and so what I expect is something like this. I'm going to start off at 0, and I'm going to see some kind of a rising waveform that looks like this. Okay, and this is going to reflect some time constant. Okay, tau time constant for this will be reflective of 2 kilo ohms times CGS. Let's assume it's a pretty large time constant. Then when VA rises again, this is going to drop because R on is very low. It's going to drop quickly, and then it's going to continue like this. Okay, so this is what you would expect. No, no magic here. Let me switch to purple for VC. So now because VB has risen slowly, what does VC look like? So VC will start off at 0 because VB is high, and then it goes up to 5 volts. And then it continues at 5 volts. And then at this point, VB starts to rise. At some point, VB is going to rise high enough to hit the threshold value for the MOSFET at the second inverter. And so because the MOSFET turns on, so as the voltage at B goes above the threshold value for the MOSFET at the whose input is B, the output is going to fall. So here at some point, the MOSFET output, okay, the second inverter output is going to fall, and then I'm going to continue on down here. And then as VB at the signal at B goes down, the output at C is going to go up again. This is what it's going to look like. So this is what we know. Okay. The bad thing that has happened here is that notice that this delay has happened. Okay, because my green signal, the signal at B rose slowly. Okay, it took some time to cross the threshold voltage for the inverter, the MOSFET in the inverter, the second inverter, and so I get some delay. Okay, so my falling happens a little bit after the signal falls at VA. Okay, there is some delay. Okay, we understand that. Okay, there's no magic here. We understand it, and this is explained by RC circuits. Okay, this is all that you know about. Okay, there's nothing new here. Okay, I'm going to show you a demo, and this is simply going to confirm what you already know. Okay, and after you see this demo, I'm going to pull the rug out from under your feet. Okay, so let's start by seeing something that we all know about.